hours. This next. So now I would like to show you that in all electrical methods, except one, electrical it means based on constant current, we always measure the same quantity, no difference. It's interesting to know. So let me show you. In this 4-electrode array, we measure resistance. When we divide voltage Mn, divide by current. Let me show next case. Next case. It looks like completely different, but in effect, the same. Borehole, layers. You have one current electrode. One current electrode on the top, B. That's current. Now, there is a receiver electrode, M. Another voltmeter, another receiver electrode. So this system in logging industry is called the normal probe. Very popular system. Distance around 1 meter. Varies, but practically 1 meter. So please imagine this system is moving. Question, what do we measure? Let us look together. Always we measure N, that's N. We measure difference of, we measure voltage between M and N. Since it's a far away, very far away, potential electrode N is equal 0. So Vmn equal Um minus Un. Since it's a far away, we are at depth 1,000 feet, 5,000 feet. We measure Um. Voltage is equal Um. Then when we take ratio, what do we measure? Um minus Un divided by current, or Um divided by current. That's equipotential surface, which is going through electrode. That's infinity. So normal probe is always, or potential probe, it has two names. In Europe, in North America, normal probe, one of the most popular probes, it measures resistance of hole medium beneath receiver electrode. Now let me show you another probe, popular probe. I am showing you not some research, but probes which were introduced by Schlumberger, brothers of Schlumberger, at 20s, and from this moment they are used widely. Let me show another probe. You have current electrode, again surface, again ampere meter, again electrode B, and now two electrodes in the borehole. Distance between Mn usually smaller than between A and M. Let us say 1.5 meter, Mn 20 centimeters. Now, what do we measure? We measure voltage between point Mn. What does it mean? Voltage Vmn equal Um minus Un. Then we divide again current. And what we obtain? Resistance between what? Between these two equipotential surfaces. Please compare with this probe. This probe is very nice. It's very popular. It gives you, when your device is moving along borehole, It shows you change of resistivity. But we are interested not only see resistivity, but we would like to detect boundaries. So this probe is more popular for this purpose. Why? Because it measures resistance, not whole medium, but only medium between these equipotential surfaces. Second popular probe. Let me show you more. What my goal is not to teach you logging. We don't have time. It's an excellent excellent subject because it's powerful industry. But it's important to see, regardless of whether it's surface or logging industry, always we measure the same. Resistance, only between what and which part of the medium. Now, let me show last example. Please, imagine pipe, metal pipe. Clear? 2 meters length. Please imagine in metal pipe hole. Hole. Please imagine inside there is current electrode. Another current electrode as usually here. Understandable? Now, please imagine instead of electrode, small electrode, this whole pipe is receiver electrode M. Then up by meter, and then electrode N. This device on the depth 5,000 feet. Now, who knows how this probe is called? I would like to know where I am. How this probe is called? No idea. So one of the most popular tools in logging industry. It's called guard lateral lock. Guard lateral lock. Guard, who is near gates. Not allowed to people go. I would like to be sure that my Russian accent would not create misunderstanding. So, what do we measure? It's a metal. Let us think together. How, if it's a metal, what we can say about this surface from electrical point of view? It's equipotential surface. Equipotential, it means because here, if there is an electrical field, it's very small, it's a metal. So mainly current from this electrode, from this hole, it goes into formation. That's mud, raw mud, that's raw formation. Clear? Very often, especially, mainly only I would say, oil industry, we have section when resistivity of mud is much smaller than resistivity of formation. Current is not stupid. It does not want to go into formation. It wants to go along of SVR where it's easy, along of borehole. But we would like to get information about resistivity of formation. So what we would like? To force current into formation. So since it's equipotential surface, current mainly go into perpendicular to the axis. What do we measure? We measure potential of the surface, UM, because UN small, far away. And again we obtain potential divided by current, resistance of what? Of this part of the medium. Since it's not conductive, main contribution comes from this part. That's another example of example of measuring resistance. I can continue and continue and continue. but always with only one exception. We do measure resistance between one equipotential surface and another. Now, that's what I wanted to show you, whether surface method or not surface, logging methods, we always measure resistance. Now, do you have some questions? I'm concerned that you don't have questions. Either it's too simple. I think it's too simple. And you know subject. Or something bothers you. Help me, because we have to spend 6 more days. I will go to more and more complicated material. This is the simple. I used it in order to bring you to more complicated and also to illustrate some very important concepts. Could you make me some would you like to give me some suggestions what I have to do in order to increase your questioning abilities? Huh?
I think it's just that it's fine, it's easy to understand.
Easier to understand. So yeah, it's very simple. I think West Mining made great mistake to invite me, because what I'm telling, everything was known and clear. So boss here, so we'll let him know truth. Yes. So let me continue. Now there is in electrical methods, there is one very important concept, apparent resistivity, not resistance, apparent resistivity. Why do we introduce it? What is it? It turns out in all methods, geophysics, electrical methods, we use apparent resistivity. And always idea of introduction, apparent resistivity, and method of introduction is almost the same. At least idea is the same. My goal to show you the idea. Let us do it. Again, it's the same for logging and surface methods. Row 1, row 2. Now, what we would like. Always it's important, first of all, to formulate what we would like, and then to do something with simple formulas. Our goal is to study geoelectrical section, correct? Correct. For example, in this case, what we would like? We would like to see this interface and to see what is the difference between resistivities, nothing else. So, let us ask ourselves with what we would like to compare our measurements. Again, remember, what I am doing is valid for frequency, transient, magnetotelluric, control source MT, for all methods without any exception. So, let us do the following. Let us mentally imagine uniform half space at this exactly the same array. Clear? The same array, the same current. When I say the same array, the same separation, everything the same, exactly the same. Now, and also we have here only we have uniform half space. Here we have more complicated medium. So what is the quantity from your point of view? I will not move, I promise you, if you don't answer this question. What is the quantity which would characterize presence of interface?
Changing the resistivity of the observed as you move the profile?
We don't measure resistivity. We measure two quantities, voltage between Mn and current AB. So we have voltage Vmn and current IAB, current in this line, correct? And voltage here. What is, you have two models, you perform measurements in two models. What is the quantity from your point of view would show how medium, or let us say, show you presence of something? Vertical change resistivity or lateral. What is it?
Change in the normalized voltage.
Sorry?
Change in the normalized voltage.
Change of normalized voltage. Okay. So let me develop your idea. First step, number one, I measure voltage normalized by current. I got what? Resistance of this medium, correct? I also measure voltage here, divide by current, I get resistance. They are the same or not? These resistances are the same or not? No, because there is a here interface. What is the, you have two pair of measurements, voltage current, voltage in uniform medium with resistivity rho 1, let me emphasize uniform, also current AB. Tell me please, what is the quantity, you have two measurements. What is the quantity which would show the first model differs from the second model?
The current?
No.
Voltage, because the current stays the same.
Sorry?
Don't you think the current the same in all these situations, so you're looking for a different voltage?
Sorry, I didn't understand. No, it's better that I didn't, to say that I didn't understand. But you see difference between you and me. Bravely say I don't understand. You see? So,
So you keep the current constant.
let us keep in both cases current is constant.
Current's constant.
Constant, 1 ampere and 1 ampere. Then I will generalize for case when they are not equal. So currents are not equal.
So the only property that can vary is the voltage.
Voltage. So what would be the quantity which shows very well the models are different?
Difference between the two voltages.
Difference. One scenario, we are on the right track. Difference. What else? Difference. Very good. So, no, we measure only voltage and current. Current is the same. We decided. But so we have two values of voltage, 3 millivolt and 2 millivolt. So suggestion, very reasonable. Let us take difference. This difference shows how to medium vary. Can you offer another quantity which also would characterize? Huh?
Where the electrons are.
No, separation is the same. Everything is fixed, the same.
Difference between them.
The difference is good, but what else could be?
And amplitude.
No, we don't have anything except amplitude. It's direct current. Ratio. Let us take ratio. Do you agree with me if I say voltage measured here divide by voltage in uniform half space, uniform, is a measure of variation of the models. If ratio 1, it means, let us say roughly, it's not exactly, roughly, they're the same, medium the same. Now, so this simple, it's almost child idea is basis of apparent resistivity, only with small difference. We never have the same current. So that's the reason why we normalize by current. So here, when I take ratio, it means voltage divided by current. It means voltage when current is equal 1. Here, voltage divided by current, it means here also the same current, 1. So concept of apparent resistivity in all direct current methods, surface and logging, is apparent resistivity normalized by rho 1 is equal voltage which we measure divided by current with respect to voltage Mn divided by current in uniform half space. Since normalization it means current the same, we simply say Vmn divide Vmn measured. So apparent resistivity normalized by resistivity of the first layer is a measure how model differs from uniform half space. Clear? Now, using this expression, we can write apparent resistivity equal rho 1 Vmn divide Vmn rho 1 uniform. That's classical expression for apparent resistivity. Nothing new, nothing special, but it's tradition. Why it's convenient? There is a good reason. But before, let me tell you, this transformation from real signals which we measure to apparent resistivity, don't add, don't subtract information. It's a pure arithmetics. So we have the same information in the field which we measure, and we have the same information in apparent resistivity. But since before we didn't have computers, we had to do by hands, by eyes. So we wanted greatly to have curves which would reflect geoelectrical section better than field itself, voltage. That was the reason why this apparent resistivity was introduced. Let me give you example behavior of apparent resistivity curves. For instance, I will give you two examples because it's subject beyond of our main direction. We have a dike. Suppose very small overburden. Suppose we have very clever array, which is used often, more often than you think, because all of us mainly involved in electromagnetic methods. Suppose we have our array AMN, B, and there is another electrode C. Clear or not clear? So electrode is perpendicular to profile. And let us say 500 meters. Put one electrode, coil, big coil, and we're moving long enough along profile and still use one current electrode. At each point, we make two measurements. Two measurements. One measurement when current travels from here to here. So we measure voltage Vm, and when current goes from A, O middle point C. Then at the same point, we change direction of the current, the force current travel from B to C. It must be closed circuit. So in a man we measure voltage as before, but battery either connected with C and B, or battery has connection with A and C. It turns out at each point we have two voltages, therefore two apparent resistivities. And graph has the following form. one apparent resistivity and another apparent resistivity. That's old, good method before, when electromagnetic are not used for detecting dikes. It's called combined profiling. Combined profiling. Everybody understand how it works? Or it's too dirty? Is it clear? Yes. Now, let me give you another example. Sometimes it's useful when there is no overburden, but there is a conducting environment, dike, very good conducting dike, and what I did forgot to tell you. And but this crossover, it's extremely remarkable feature. Usually above this dike you see, if this, it's called conducting crossover. Because when you have conducting dike, these two apparent resistivity curves intersect exactly above. Since again environment is complicated, we are looking for good features. It's called combining profiling. Yes?
Is the intersection above the center of the dike?
Yes, exactly above.
Is that independent of the dip of the dike? Or is it?
No, it doesn't depend. It normally depends, but crossover, no. Again, it's a conventional method. Now let me one more example, we will move to other areas. My goal to now review, nothing else. Let us take two-layer medium, rho 1 and rho 2. Electrode A, M, N, and B. Horizontal layer medium. Horizontally layer medium. Let us, as physicists, first of all, and then as geophysicists, to work. There is a current, therefore, where charges arise? On the surface of electrode. Then negative charges on the surface another electrode. Where else charges arise? You remember this lovely formula? Here. Sign depends on ratio rho 2 over rho 1. Then, where else? Oh, there is a charges. They create electrical field near Earth's surface. Charges arise here. So at all interfaces, what do we measure? We measure total voltage due to electrodes, primary field, plus secondary field. Which part contains information about rho 2? This part. This part depends on what? Rho 1 due to electrode. We know this part. It's a function rho 1. Now I would like to ask you, I will remove this plus and minus. A, M, N, B, rho 1, rho 2. Tell me please, when electrodes are, distance between them is very small, which part of the field is stronger? Primary or secondary? Primary. So therefore, transforming apparent resistivity, voltage apparent resistivity, we obtain rho 1. Then we increase separation. We increase influence of rho 2. Old story which was started in bathroom of brothers of Schlumberger. And exactly at the middle between 19th and 20th century, that's how they invented Schlumberger soundings. Now I would like to discuss with you one more question, because we need it, badly need, for magnetic fields. Suppose we have inhomogeneity on the Earth's surface or inside, doesn't matter. That's rho 2, rho 1. Suppose we create electrical field. B. Current goes in this direction. As we know, electrical charges arise here. If it's more resistive, that's more conductive. Now it's interesting to ask ourselves. Now it's preparation, it's not discussion for interpretation, only preparation for next part. Let us discuss behave electrical field inside. Ready? It turns out that electrical field consists of two parts. Part number one, primary electrical field, E naught. Also, what else? Don't forget, we don't discuss electrostatic induction. No more electrostatic induction. When field inside is equal to 0, when surrounding medium is insulator. Now we are working with conducting medium, so completely no more room for electrostatic induction. So these charges also create electrical field. In this case, how secondary field inside is directed? In this case, more resistive target. From plus to minus. So total field will be equal primary plus secondary. Clear? Now, let us take opposite case. More conductive target. Rho2 less than Rho1. What kind of charges here arise? Here arise negative and positive charges. So total electrical field, any component, I don't write vector, would be primary electrical field caused by these electrodes, but now how secondary field will be directed? Opposite. Magnitude. So now let us study this question because it's an important question. It will be transformed into electromagnetics. Now, for understanding, only for understanding, please imagine ellipsoid or spheroid. With cross-section spheric. It turns out that if, let us call axis B, that's axis A. So here positive charges, here negative charges. That's Rho1, Rho2, or gamma 1, gamma 2. And theory shows electrical field inside is equal. Along, electrical field, along. Equal primary electrical field, unit plus gamma 2 minus gamma 1, divide gamma 1 times some factor, geometrical factor. Let us discuss. Again, I don't derive, I only tell. So electrical field inside is equal primary electrical field unit plus this ratio conductivities times factor which depends only geometry. Only geometry. Let us think together because we will use that's basis for missile mass, for example, and many other things. So let's watch. First of all, this factor, L, has one interesting feature. when ratio A over B, ratio of semi-axis, clear? A and B. When A and B becomes very, very large, this factor goes to 0. What happens when in the limit I start to increase? What happens with this body? It becomes a cylinder. Correct? And our primary electrical field has this direction. So what would be the electrical field inside in this case? So that's an important subject. Let us slowly discuss. Case number 1. Case number 1. And you will understand what is going on. It's physics very simple. Case number 1, A over B goes to infinity. Ellipsoid transforms into dike or pipe, which is very long. What would happen in this case? A goes to 0. What happens with electrical field inside? It becomes equal primary electrical field. What does it mean? When you extend, but let us consider this case. We have primary field and we have secondary field for conducting dike, correct? So charges which arise at their face create electrical field which is opposite to primary. It's trying to decrease electrical field inside. That's the reason why it's called depolarization effect. No polarization, but tradition from magnetics, it's called depolarization effect. Simply, electrical field inside is caused by primary minus secondary. When you extend your dike, your body, these charges are going away, and field approach to primary field. Now, I am going to use it tomorrow, not today. Now, let us consider influence of conductivity. What would happen if conductivity surrounding medium is equal to 0? Unrealistic case, but let us do it. What would happen with electrical field? Conductivity of surrounding medium goes to 0. You are tired, perhaps? So if gamma 1 equals 0, what would happen with electrical field inside? Sorry? So conductivity of surrounding medium goes to 0, so surrounding medium becomes insulator. So what happens with electrical field inside? 0, bravely 0, because gamma 1 equal 0, infinity, that's it. No surprise. Now we observe electrostatic induction because surrounding medium insulate and field inside will be 0. No way to create currents. I am approaching to magnetic field of current. Now, so let us assume for a moment, gamma 1 is very large. Now, opposite case. Gamma 2 is very large, I'm sorry. What happens in this case? Suppose gamma 2 is very large. So I consider case very high contrast. Let us look together. In this case, electrical field will be equal E naught, correct? Times, we can neglect by this term, gamma 1 much less than gamma 2. So can write E naught, gamma 1 divided by gamma 2. So with increasing, I hope this factor we didn't lose. So L, factor L. So when you have very good conductor, electrical field inside is small, but we are not worried about it. Why? Because we make some preparations. Now I would like to do something else. So that's one case, that's second case. Now I would like to ask you, let us find out current inside. Current inside. In this case, how to calculate current density inside such conductor? Current density will be equal what? Gamma 2 times electrical field. Gamma and gamma 2 will cancel, and what would happen? Current will be proportional to what? Conductivity of when we multiply gamma 2 cancel, and it turns out that electrical field current density will be proportional instead of conductivity of dike to conductivity of surrounding medium. So all these effects for us is not important now, but tomorrow when I start to explain you behavior of magnetic field, it would be extremely important. For instance, if you remember our first example, dike, and I created electrical field along. How different story. What we found out, what is the electrical field inside in this case? Do we have charges? In this case, when electrical field along of strike? No. So electrical field inside is the same as outside. It's a primary electrical field. Now I would like to find current. If conductivity is very large, we will create here very strong current, very strong current. That's the idea of Miss-Salamas in classical way. And later I will give you different scenario, different application of this. Now, do we have time or we have to make break?
You have a break now or it's only 5 minutes?
5 minutes we have?
Yeah.
Okay. Now, I prefer to continue. So, what I discuss with you is electrical field inside of conductor consists of two parts. Primary electrical field, regardless how we create it, and secondary, due to charges which arise at interface. These charges, if conductor is good conductor, trying to decrease electrical field. So if it's elongated body, their influence is very small. And that's we will use it. Now, as I told you, Coulomb's law is valid for electromagnetic fields. Therefore, what I described is applied for electromagnetic fields. And let me briefly, during 4 or 5 minutes, tell about this part. We have a method, magnetotelluric soundings. We measure electrical field and magnetic field and take ratio between electrical and magnetic field. That's called impedance, E over B, Ex, B, Y. What I told you about influence of inhomogeneity remains valid for electromagnetic fields. So this is a called galvanic part of the field, but my respectable friend will speak about it. So this part of the field very often plays very, very important role. So since I am not going to speak in detail, only emphasize this fact. Now another situation. We have surface inhomogeneity, rho naught, rho 1. We have electrical field. Charges don't care what created this electrical field. Electrode, or currents in ionosphere, or field of radio stations. They don't know anything. That's what we do know. They don't know at all. As soon as there is electrical field, instantly here charges arise. And these charges do create electrical field. And this so we measure, for example, suppose we have a horizontal layer medium, and we have this inhomogeneity. It turns out electrical field consists of two parts, field in horizontal layer medium plus this field due to these charges. It turns out in magnetotelluric soundings we measure different frequencies, high frequencies, low frequencies. If we would not have this inhomogeneity, we would be able to go to look through this medium. It's known, I will explain later, with decrease of frequency, depth investigation in horizontal layer medium increases. However, there is inhomogeneity. Regardless what is the frequency, charges sitting here, swamp, fraction zone, and this effect is formidable obstacle for many electromagnetic methods. First of all, for magnetotelluric soundings, and also for controlled source MT. From physical point of view, it does not differ from what I explained. Only these charges depends on time, but at each moment they do create electrical field according to Coulomb's law. That's small introduction, which we will discuss later. Number 2, constant magnetic field. Let us recall everything what we know, because without them we will not be able to approach to Maxwell equation in electrodynamics. So far we spoke only about electrical field, and then I briefly tried to think about currents, their behavior. We need it for the next part. Now, magnetic field. What creates magnetic field? Constant magnetic field. Sorry? Which? Moving charge. Very good. So how we call it? Current. Current. We notice these charges are moving very slowly, but it's amazing. In spite of their velocity, 10 minus 7, 10 minus 8 meters per second, for every normal human being, they don't move. What is the velocity? 10 minus 7, 10 minus 8? Nothing. But still, the fact that they are slightly moving, already calls for second field, which we should consider magnetic field. So, our subject, magnetic field, B caused by currents. who was the first who discovered the fact that magnetic field is caused by currents? Do you know? Name. Huh? No. Huh? Ampere was extremely clever scientist who discovered, as Coulomb discovered that electrical field is caused by charges, established this physical law. The Ampere established that currents create magnetic field. So it's movable charges, slowly, awfully slowly, but that doesn't matter. Now, Ampere has much more complicated task than Coulomb, much more complicated. Why? Because how you can, in gravity or in case of electrical field, you can take two charges and find out force with which one charge acts on another. But how to establish relationship between magnetic field and currents, or in other words, between interaction between currents? You have to take two closed circuits and watch how one circuit creates mechanical force on another. It depends on many factors. It depends on shape of the contour, mutual orientation, size, direction of the currents. So it's extremely, if you have small imagination at this moment, if you're not tired too much, imagine two contours. What you can do, only one thing, to measure mechanical force with which one contour affects current on another. That's what Ampere established, and moreover, in spite of in spite of that many factors affect on this force, he was able to establish the law which has his name. Let me discuss with you this law. So we have two contours. Contour current 1, current 2. He found out in laboratory that if there is current in both paths, each of them feels presence of another. Each contour wants to move, which contour wants current contour would like to be deformed. So it was extremely difficult to find relation between force and shape of the contour, currents, mutual position. So he made genius guess. Suppose we have two current elements. Dl, length, and vector which shows direction of charges. And there is another element, I2, dl2. Suppose that's point Q, that's point P. No way to force current to move through piece of wire which is not closed. No way. So he invented this experiment. He assumed, let us assume we can create current in these two elements, and no way to check him directly. And then he told mechanical force with which one element, current element, acts another is equal mu naught 4 pi I1 I2 dl at point P cross product dl point Q cross product LQP divide LQP cube. That's point Q, that's point P, that's LQP, that's force, not B, but dF at points P. So force with which this element acts on another equal constant. It's called sometimes magnetic permeability in free space, does not it's not proper name, 4 pi, product of currents and cross product of one vector, another vector, twice cross product, divide cube distance. That was the beginning of all theory of magnetic fields. So, how to check? How Ampere's law was checked? Directly? No way. But using this equation, it's possible to calculate force with which one contour acts on another using principal superposition. For instance, you take one element, GL, calculate force with, take another element, find force with which, according to Ampere's law, then perform summation, find force caused by all other elements. Then take total force, double integration. Unpleasant business. But it was done. It was done. There were no any wave last century. And up to now, there is no one experiment which shows that Ampere was wrong. So unlike Coulomb's law, that was done for case which cannot be checked directly, but all the results of interaction of current contours supports his genius guess. Now, tell me please, where do you know this law is widely used in techniques? Forget about geophysics for a moment. At all. Where in technique, it's a simple question. Very simple. Are there areas in techniques where this law, Ampere's law, is used widely? Don't. Huh? Of course, motors, yes. Motors, yes. That's exactly, that's where it's used. You have stator, you have magnet, you have current, it starts to rotate. That's the basis. So no jokes. Without it, it will be hard to imagine where we are now. So, using this equation, by analogy with Coulomb's law, magnetic field was introduced as force caused by current. And the second relation, which is simply comes directly from here, is if I have element with current, I, GL, then magnetic field is equal mu naught I GL LQP divide LQP cube. For pi, not too bad to forget. So what is written here? If I have element with current, at each point there is magnetic field. How it's directed? It's written here. If that's current element, at this point, what would be direction of magnetic field? What would be magnetic field at this point? 0. So very known facts, and we use it. That's magnetic field due to current element. If we have current loop, we always have current loop. Please take integral from it and you will find magnetic field. Now, what is the unit of measurements of magnetic field? Gamma, or Tesla more precisely, but Tesla too big for our purposes. So we are dealing with 10⁻⁹ of Tesla, nanotesla, or gamma. Now, let us speak about this law. Complete analogy with Coulomb's law. I have a current loop. I can calculate magnetic field. Now, if I put this current loop into magnetic medium, what happens with magnetic field caused by this current? Will it change or not? Again, I have current loop. There is a current, 1 ampere. Now, instead of free space, I will take magnetic medium, paramagnetic, diamagnetic, ferromagnetic. What would happen with magnetic field caused by this current loop? You must treat it. It remains the same. Because again, no physical properties. Please don't pay attention, mu naught. It's a constant. It's not magnetic permeability of free space. There is no such quantity as the electrical constant of free space. Free space, it's nothing. Does not exist, so it cannot have physical properties. So that's first fact about magnetic field. You see, complete analogy with Coulomb's law. No influence of medium. If you have constant current, given current, it will give everywhere the same magnetic field. Good. It means we can use this law for our medium, for other cases. Now, it turns out that it's valid not only for constant current, but practically for all electromagnetic fields electromagnetic methods which used in frequency time domain. So not too bad to remember as Coulomb's law. They are much more general than we think about it. Next moment. Now, what creates magnetic field? Current. All currents are closed. So Biot-Savart law tells us generator of magnetic field, closed currents. Now, what happens if you have, let us remember it. Let us take magnetic material. Piece of magnetic material. Tell me please, does it create magnetic field or not? Again, it's a review, it's not a review. Does it create magnetic field or not? So no current with loop, simply I took a piece of steel, for example, iron, or from iron pipe. Does it create magnetic field or not?
No.
Why not? Or when it creates? Are there cases when creates magnetic material field? Are there cases where it don't create?
It depends if it's got a magnetic moment or a magnetic dipole.
What does it mean magnetic dipole? What does it mean magnetic moment? Let us discuss. It's a good direction because that's our also goal. What is I have magnetic material. Sometimes there are circumstances. Let me heat it. Let me heat, make warmer. Let me take magnetite, for instance. Let me warm up to 600 degrees Celsius. What happens? Does this piece of material creates magnetic field or not at such temperature?
No, it's above the Curie point.
Yes, exactly. What does it mean from physical point of view?
You totally randomise the alignment of the material within the magnetite, so it hasn't got a specific moment. It's totally random.
Very good. So what really happens? What creates, when we above, below of Curie point, do we have magnetic field caused by magnetite? Sorry?
If the moments are aligned.
If there is a moment. What does it mean there is a moment? What is the physical cause? My goal is to relate with this equation, which is called Biot-Savart law. Now, what creates, when you say moment, what do you mean?
The internal crystal structure of the magnetite is consists of tiny north-south poles, and if they're totally...
Poles. What does pole mean?
Separation of charge.
What kind of charges?
Spinning.
Not magnetic charges or magnetic charges.
Electron spin.
Huh? Very good. But when you mention charges, you mean electrical charges or magnetic charges? So,
Only electrical charges.
huh? Electrical charges. So, we are talking about motion of electrical charges. How we call this motion of electrical charges? Current. So, even we are going to inside of magnetite, we have to remember that magnetic field caused because there are molecular currents and nothing else. What does magnetic dipole mean? What is it? Magnetic dipole. Well, very often everybody uses magnetic dipole, magnetic moment. What is it? But if I ask you simple question, what does magnetic dipole mean? Huh? Sorry?
Current filament. It's analogous to current.
Current filament. Very good, but provided it's true if one condition takes place. What is the condition? No. Now, you see, last hour, so I will not teach. I will ask questions, and then we will be prepared for tomorrow. So, again, what is the behavior of normal magnetic field, constant magnetic field on the Earth? But if I ask you, you told me there is magnetic field 50,000 gauss. 50,000 gauss. It's at all points the same magnetic field or not, or changes? Changes. How it changes?
Magnitude and direction.
Is there some equation which describes its change? Beautiful equation. It's used widely in electromagnetic methods everywhere.
The idea.
Huh? No, too complicated for me. Something simple. What is the equation?
The International Geomagnetic Reference Field.
Yes, but 95% of this field is described by field of magnetic dipole. So what creates magnetic field on the surface of the Earth? Currents. Where there are? Oh, so far away. Far away. How far? What is the radius approximately of this current filament? It's a small or it's very large? Huh? Oh, 2,000 radius, 2,000 kilometers at least. How far we measure from this current filament?
3,000 kilometers.
Oh, radius of the Earth a little more. Around 6,000. So what happens? Let us combine these two facts. Let us be empirical at the end of our class, our discussion, lectures. On one hand, we do know normal magnetic field with good accuracy is called magnetic field of dipole. Correct? On the other hand, we know these currents are located far away from point of observation. So let us combine both facts and call each current loop, not necessarily circle loop, current filament, creates field of the magnetic dipole if we measure where? Far away. That's all. That's magnetic dipole. when I have in electroprospecting two electrodes, A and B, here positive charges, here negative, distance L. If I measure far away, how this system is called? Electrical dipole. When here we consider electrical dipole, bravely we can say system of two charges with the same magnitude, different sign, creates far away with respect to distance field of electrical dipole. In magnetics, no way to think about magnetic charges. Magnetic dipole, when we say word magnetic dipole, it means simply field of current loop or system of current loops if we measure far away with respect to their dimension. So when I ask you about magnetite or ferromagnetic material, I meant that magnetic field, if we feel effect from magnetic medium, it's due to the fact that orientation of these molecular currents is such that together they at each volume create non-zero magnetic dipole. Clear? When you told me, or together we discuss about warming up, it happens that due to heat, all these dipoles are distributed randomly, and magnetic dipole is equal 0. Now, what really moment of magnetic dipole mean? So we know what does magnetic dipole mean, current circle. And now my question, what is the moment of magnetic dipole? What is the quantity? It's equal to what? First of all, it's scalar or vector? What is the magnitude of this vector?
Area times the current.
Area times the current, very good. Area times the current. Moment, M, equal current times area. True? And not too bad to put unit vector up if current goes counterclockwise. That's iron rule. That's magnetic dipole. Now, let me ask you a question. We have time. What is the difference between a remnant and an inductive magnetization? Is there principal difference between two of them? Or it's practically the same from physical point of view?
When you've actually got the when you've actually induced the magnetisation, it's the same. But when you take away what's induced it, then it goes back to being non-magnetic. The remnant magnetisation is permanent, regardless of whether you use the secondary current. But
for example, let us imagine there is an earthquake. It was millions of years ago. Lava is moving to the bottom of the ocean. It happens many millions of years ago. Lava is laid on the bottom. What happens at this? What happened at that moment?
Goes through the Curie point.
Yes, exactly. When there was magnetic field before, correct? There was magnetic field before. When temperature becomes low, Curie point, that magnetic field was doing with molecular currents? Align it, exactly, according Biot-Savart law. If I ask you, there is molecular current and there is magnetic field, what do you think, what would be orientation of what happens? Please imagine the following situation. You have current, molecular current, I, and you have magnetic field B, magnetic field of the Earth. How this loop would be oriented?
plane of the loop is perpendicular.
Exactly. If your current loop will be in the plane of the field, what would be direction of the forces? One this way, another this way. Ampere's law. That's I'm trying now and then to give you examples how everything is important. If you imagine molecular current in this way, a magnetic field along, it would be not stable position because current goes this way, magnetic this way, force will go perpendicular. Here in opposite direction, and molecular current will take position in such a way that magnetic field will be perpendicular to the plane. What would be direction of the moment of this dipole? A long field in the same direction of the field or in opposite?
Opposite.
Huh?
This was not.
It depends, diamagnetic material or paramagnetic. In a paramagnetic along, in diamagnetic opposite. That's all. Now, very good. Now, we have a few minutes more. Now, who knows what does paleomagnetic? First of all, what does it mean North Pole, magnetic North Pole, and South magnetic pole? What is it? You see how it became simply after Curl divergence. So, let us say north magnetic pole. What is it? Point, masses, magnetic masses. What is it?
Is it the point at which if you consider the magnetic field as lines of flux, it's the point at which they converge in your pretend dipole?
Could you develop it? Because I'm not sure that I'm. So.
You draw some lines of magnetic flux, the point at which those lines of flux converge.
Where they should converge? No. If I understood you correctly, maybe I'm wrong easily. But are there other suggestions? What is this north and south magnetic pole?
The magnetic moment is perpendicular to the surface of it.
Now, there are currents in the core, you told me. Did you tell me it or not? Huh? I don't know, I forgot everything. So, you told me that magnetic currents in the core, according to Biot-Savart law, create magnetic field of magnetic dipole. So, these currents are characterized by magnetic moment. How this magnetic moment of Earth currents is directed? So there you told, I don't know, that's current loop, that magnetic dipole, moment M, area times current, is directed perpendicular. Correct? Now let us draw this line to the Earth's surface. How many points we will get? 2. That's north and south pole. Clear? Now, but that's not, let us refresh here. Everything according to Biot-Savart law. Now, that's not end of your suffering. Now, question is, do you know what does paleomagnetism mean? Can you explain me principle of paleomagnetism shortly, using concept of magnetic dipole? Peter, how many minutes we have?
How are you going?
I need 15 minutes. Is it okay? 15 minutes. Okay. Now, so you will think how to explain me. I will write only expression for magnetic dipole. So magnetic dipole is extremely important concept, electromagnetics, But now we speak about global problems. Now we are in the vacation. We don't need to think seriously. So let us speak about global problems. So, field of magnetic dipole has amazing simple feature. Again, remember, what I am telling is true for all electromagnetic practically methods, except radar and the electrical logging. Dipole. At each point, magnetic field of the current, this current, regardless small or 1,000 kilometers, only one condition, measure far away with respect to radius. Magnetic field, how many components magnetic? Let me take spherical system of coordinates. That's direction of the moment. That's R. Question, how many components magnetic field has in spherical system coordinates? 2. Which one of them is radial component? BR. Another? Is it correct? B theta. So let us write expression. BR and B theta. BR equal 2 mu naught M 4 pi R cube. What about angle? Theta. Help me. Quickly help me, please, because it's a very important in electromagnetics, in global geophysics, in paleomagnetism. But what is dependence on angle theta? Intuition. We are talking about very fundamental concepts. Cosine theta. Very simple. What be theta? Mu naught M 4 pi R cube sinus theta. Clear? The same happens with coil if you take laboratory. The same it happens with many our systems which we use. Surface, logging. That's expression for the dipole. Now, ready. How magnetic field behaves along axis? Which component is equal for sure 0? Which is equal 0? This component or this component? B theta is equal 0. B theta is equal so. Now, so at this point magnetic field had directed up. How is directed here? What do you think? You can come to conclusion as you using different ways. So loop, small loop, I'm asking about simple facts. How magnetic field directed above and beneath along axis? Still up. Still up. Because it means if theta pi it's my minus unit, it means opposite to radius, up. Now, that's first question. Now, that's called equatorial plane. How magnetic field is directed at equatorial plane? Which component is equal to 0? BR. There is only B theta. So it's directed down. Moment up, field down. 2 vital features. Now, last, the most important. Let me take radius. Arbitrary radius. How magnetic field changes along any radius? Inverse proportion cube distance. That's clear. Understandable? Because theta remains the same. Now, more difficult question. Tell me, please. I take arbitrary point. That's BR. That's B theta. What is it correct if I write that's direction of total vector. True? Now, very important. If you understand it, you would tell me about paleomagnetism. Now, let us call it angle alpha. Question. Please, I know you are tired, but let us try. How this angle between radius and field changes when I measure at different points? You understand my question? Magnitude for sure decreases how? Unit divide r cubed. Now my question, I have here magnetic field total, here that's magnetic field total. I would like to know how this angle alpha changes depending on distance r. Sorry? Can we do it? Can we solve this extremely difficult mathematical problem? Let us, what is the component? What this component? B. This component, B. So can I say tangential alpha equal what? B theta over BR. True? True or not? So can you look in this B theta over BR, save my time, my efforts, take ratio, what would happen? 4 pi out. R out. What is left? Where we are? Sorry, I'm in trouble. Equal 1/2 tangential theta. So, conclusion.
Alpha is constant for any theta?
For any theta. So, if you take one radius, regardless how close, how far, we have the same angle between total vector and radius. Clear? Now, let us recall for a moment what is the theta? Angle between what? Radius and moment. What is the alpha? Angle between direction of the field and radius. Now, let us ask ourselves. We came to everything what I'm trying to do now, illustrate importance Biot-Savart law beyond electromagnetic methods, because it's a very general, very important information. Now, you are on the Earth's surface. You take sample of the rock. Suppose you have device which defines, age of this rock. Now, can we determine if there is, can we determine direction of remnant magnetization? That's the goal of paleomagnetism. Take sample and find, if you can, sometimes we can, sometimes we can't, but let us consider normal, favorable for paleomagnetism situation. So can we find direction of remnant magnetization? We can. Only recently, 10-20 minutes ago, we came to conclusion magnetization is directed along the field which created this magnetization millions of years ago. So in effect, we know direction of magnetic field at that time, millions of years ago. But we would like to know where was Paul at that time. That's one of the goals of magnetization. So what we have to do it? What is the angle? Alpha. Alpha angle between field which was at that time and radius. Can we find direction of the moment of current in the earth at that time? Solve this complicated equation. Alpha you know from experiment, then you can calculate theta. Draw theta from center and you will get what? Direction of the moment at that time. When you draw perpendicular, you came here, you will find what? Pole. At that time, that's how we watch for movement of the pole. What I wanted to tell at the end, that simple concept of magnetic dipole is extremely useful in paleomagnetism. Tomorrow it will be useful for electromagnetic methods. But very simple, also only not too bad to know field of magnetic dipole, primary field. This expression are valid for all quasi-stationary fields which we are going to consider next week. Let me finish today. So everything going very well. Tomorrow electromagnetic fields.